In this class, we have to discuss another kind of reaction that an ether can offer. So this reaction is a Claisen rearrangement reaction. So in this reaction, an allyl phenyl ether, allyl group is CH2 double bond CH2 is an allyl group, and then phenyl group C6H5 group. So an allyl phenyl ether is heated to about 200 degrees centigrade. In the absence of any catalyst or any other reagent, it undergoes a molecular rearrangement to give ortho-allyl phenol. So in this reaction, we take an allyl phenyl ether and then just heat it at 200 degrees centigrade. Then we are getting ortho-allyl phenol. The ortho position of the phenyl group is getting attached by a rearrangement reaction of allyl group from here. Okay, and this kind of reaction is known as Claisen rearrangement. So in this reaction, we are not using any catalyst, we are not using any other reagent for the reaction to take place. Just to heat at 200 degrees centigrade, a rearrangement of allyl group is taking place to the ortho position of the phenyl group. So we are getting the final product as ortho-allyl phenol. And a detailed study of the reaction shows the following. So they have studied how actually the reaction is taking place and what is actually the mechanism of the reaction. So in Claisen rearrangement, the allyl group migrates invariably to the ortho position as long as the ortho positions are not substituted. So in this case, you can see that the two ortho positions are vacant. There is no other substituents. Okay. So when this kind of rearrangement is taking place, the allyl group has the possibility to migrate towards the ortho position. So that is what here we are getting ortho-allyl phenol. There is an inversion of the allyl group during the rearrangement. Inversion in the sense, here as you know, the numbering can be given from 1 to 3. When the allyl group is attached to the ortho position or rearranges to the ortho position, actually this carbon 3 is attached to the carbon of the ortho position of the phenyl ring. Okay, and then this double bond shifts here. Okay, actually first carbon is attached to the oxygen here, but in the rearranged product, the third carbon is attached to the ortho position of the phenyl ring. So that's what the inversion has taken place. Third point, the carbon atom 3 in the starting compound gets linked to the aromatic ring in the product. This is what we have just explained, and this is proved by isotopic labeling studies. For example, like isotopic labeling in the sense we can use isotope of carbon here. Okay, so if this is starred carbon or isotope carbon, and then we do the reaction, then we can come to know by analyzing the product, we can come to know this carbon atom is the 3 carbon atom in the starting material. Okay, so from these studies it can be proved that the inversion of the product is taking place. So the reaction is shown here. Allyl phenyl ether, just heat it, then we are getting this product. So how the reaction is actually taking place here, as you know, a carbon-carbon double bond is there, it shifts here, and then this carbon double bond shifts here and this shifts here. Okay, so this will become O minus, and this carbon CH2 CH double bond CH2. Okay, this is what we are getting. Okay, so the third carbon atom is attached to the phenyl carbon. Okay, and if we consider another molecule, this is crotyl phenyl ether, crotyl group CH3 CH double bond CH2 is the crotyl group, and then phenyl group here, and so this compound is crotyl phenyl ether. And this is also example for a thermal rearrangement reaction. And here also what happens is a carbon-carbon double bond is here. This will attack this carbon atom, this carbon atom, this will attack this carbon atom, and this bond will shift here and this bond will shift here. Okay, so here this carbon attached to the phenyl carbon. So this carbon attached to the phenyl carbon, and then one CH3 is attached to this carbon, and that CH3 is shown here, and what remains rest is a CH double bond CH2. Okay, so here we are getting orthomethyl allyl phenol. When both the ortho positions of the allyl phenyl ethers are occupied, the migration occurs to the para position. So if you take another example of a compound of allyl phenyl ether where the both ortho positions are occupied, then the migration is taking place to the para position. Okay, so here we have taken a compound allyl 2,6. So this is 1, 2, 3, 4, 5, 6. 2,6 dimethyl phenyl ether. Dimethyl phenyl ether. Okay, so this is on heating. So this allyl group cannot migrate to the ortho positions because the ortho positions are occupied. Then of course it can only migrate towards the para position. Okay, so here we are getting the migrated product as for allyl 2,6 dimethyl phenol. And next point is, when the rearrangement is studied using mixtures of allyl phenyl ethers. Okay, so they have taken different allyl phenyl ethers in the reaction system itself. For example, they have taken this compound. Okay, and then they have taken another compound like this, or they have taken another compound like this. So the respective product, what we are getting here, the respective products are only formed. There is no cross reaction possible. Okay, so when you take these two compounds in the same mixture, we are getting this group is not migrated to this phenyl group. Okay, or this group is not migrated towards this phenyl group. So if this group migrates to this phenyl group and this group migrates to this phenyl group, we get a cross product. But if you take these two different allyl phenyl ethers in the same reaction system, we are getting the respective products only. Okay, so on the basis of this reaction, there is no formation of crossed product, indicating that the mechanism is intramolecular. So within the system, the reaction is taking place within the system. Intra means within. So there is no interchange is taking place. So the mechanism, on the basis of the above observation, the following intramolecular mechanism has been suggested. So effectively, in this case, the bond cleavage is not actually taking place in such a way for that particular allyl group moves from one molecule to the other one. Okay, so the reaction is taking place within the molecule. The bond breaking and bond making is taking place within the molecule. Okay, so this is an intramolecular mechanism. Okay, so here what happens is this pi bond shift here. So a bond formation is taking place with allyl carbon. Okay, and then carbon-carbon double bond of the allyl group shift here. Okay, and then this will become an O minus or carbon oxygen double bond is formed here. Okay, and the hydrogen present over here, carbon hydrogen bond shift here, and then this will become OH. Okay, so this is what actually the mechanism is, or this is the intramolecular mechanism of allyl phenyl ether or Claisen rearrangement. Next, we have to discuss a method for the estimation of methoxy group. It was developed by scientist Ciesl's method of estimation of methoxy group. The estimation is based on the reaction of compounds containing methoxy group with concentrated hydridic acid to give methyl iodide. So we have already discussed the reaction between an ether and concentrated hydridic acid. So here we are getting methyl iodide as one of the product, which quantitatively react with alcoholic silver nitrate to give silver iodide. So when we react a ether that contains CH3O methoxide group in the presence of concentrated hydridic acid, we get alcohol and methyl iodide. And this methyl iodide further reacts in the presence of silver nitrate, so it will give silver iodide and methyl nitrate. And this silver iodide precipitated will be collected and is washed, dried and weighed. From the weight of silver iodide formed in the reaction, we can calculate the number of CH3O group or methoxy group. Okay, and if we take aryl methyl ether ArOCH3, methoxy group is present. Concentrated hydriodic acid, we are getting phenol and methyl iodide. And this methyl iodide reacts further with silver nitrate, then we are getting silver iodide. Again, as we had seen, as we had done silver iodide, treated silver iodide here. Here also we have to treat silver iodide by collecting, washing and then dried. Okay, and then weighed it. Then from this we can come to know the number of methoxy groups present in the compound. Okay. The stoichiometry of the reaction follows the relationship. How now we have to come to the calculation how actually the methoxy groups are estimated. So here 1 mole of silver iodide equal to formation of 1 mole of silver iodide equal to, if we get 1 mole of silver iodide, that indicates only 1 methoxy group present in the molecule. Okay, so if we get 1 mole of silver iodide after the reaction with the silver nitrate, that indicates only 1 methoxy group. Okay, so the number of moles of silver iodide obtained starting with 1 mole of the compound gives the number of methoxy group. So when you take 1 mole of the compound and then that is treated with the silver nitrate, then we are getting silver iodide. Okay, so the number of moles of silver iodide has to be calculated, and the number of moles of the compound also, silver iodide formation, can also be calculated. Then from there we can calculate the number of methoxy groups. Here the calculation is like this. The mass of, for example, we just consider the mass of the sample is M1 and molecular mass of the sample is capital M. From this, number of moles can be calculated. Weight divided by molecular mass will give you the number of moles. M1 divided by M, number of moles of the compound. Okay. Now the mass of the silver iodide is M2. Molecular mass of the silver iodide is 234. Okay. So the number of moles of silver iodide is M2 divided by 234. Okay. And then it is written here. Therefore, M1 divided by M moles of the compound. So this is the number of moles of the compound equivalent to M2 divided by 234 moles of silver iodide. This much moles of silver iodide. So this is equivalent to M2 divided by 234 moles of the methoxy group. Okay, understand? And then now we have to calculate the 1 mole of the compound contains 1 mole of the compound. So instead of M1 divided by M, I just put 1. Okay, 1 mole. So instead of this 1 mole of the compound contains equal to, so what we have to do is, if you want to make it 1, this should be multiplied with capital M divided by small m. Okay, so if you multiply capital M by small m here on the left hand side, here also you have to multiply it with capital M and by small m1. Okay, so then we get 1 mole of the compound. So 1 mole of the compound equal to or equivalent to M2 divided by 234. So here we multiplied left hand side with the capital M divided by small m1 in order to make it 1 mole. Here also we have to multiply it with capital M divided by small m1 moles of the methoxy group. Okay, so the number of methoxy groups in the compound equal to M2 capital M divided by 234 into M1. So this will give you the number of methoxy groups present in the compound. Okay. Next we have to discuss epoxides. Epoxides are 3-membered cyclic ethanes. We have already discussed. They are also called as oxiranes. Okay. And then how we can prepare epoxides? There are mainly 2 methods for the preparation of epoxides. First method is epoxidation of alkenes. So the starting material is alkene. It should be epoxidate using per acids. Okay, so first reaction, if we take propene, CH3, CH double bond CH2 reacts with the perbenzoic acid. Perbenzoic acid means C6H5, C double bond O, OOH. Okay, so the C double bond O, OOH is the peroxy acid. So since this is phenyl group is attached here, this is perbenzoic acid. Okay, and then the extra oxygen in this case, or the per acid, one oxygen from the per acid will form a epoxide with carbon-carbon double bond of the alkene. Okay, so here we can see that CH3, CH, CH2, and then it forms a oxygen, and we are getting the benzoic acid as the byproduct. Okay, and if you take another example, butene, CH3, CH double bond CH, CH3. So the epoxide forms only at the carbon-carbon double bond. Okay, so here peroxyacetic acid, so we have used peroxyacetic acid CH3, C double bond O, OOH. Then we are getting CH3, CH, CH, O, CH3. This is 2,3 butene oxide and then acetic acid. And if we take another example, a cyclic compound, 3-methyl cyclopentene. 3-methyl, third position, can be numbered as 1, 2, 3, 3-methyl cyclopentene. So this compound is cyclopentene, and then this is reacting with perbenzoic acid. Okay, so this is perbenzoic acid, C6H5, C double bond O, OH. Okay, and then carbon-carbon double bond is here, so this forms a epoxide here. So this is 1, 2 epoxy 3-methyl cyclopentane. Okay, 1, 2, 3. So this is first we have to give this one 1, 2 epoxy 3-methyl cyclopentane. Okay, and then benzoic acid. Next is preparation from halohydrin. Halohydrin in the sense, this is hypohalous acids, like instead of HCl we have an OH group and Cl. Okay, or halogen. OH group and halogen is the hypohalous acid. The starting material is an alkene only. The halohydrins are compounds formed from the addition of hypohalous acids and alkenes. Okay, so halohydrins are the compounds which formed by reacting with hypohalous acid. Hypohalous acid is OHX, and then reacting with an alkene we get halohydrins. Reactions of halohydrins with a base gives epoxide by the elimination of a hydrogen halide, HX. Okay, so reaction scheme is shown here. You can easily understand from the reaction. So here we have ethylene, CH2 double bond CH2 plus hypochlorous acid OHCl, chlorine and water, and then we get CH2OH, CH2Cl. The OH group of hypohalous acid is attached here, and halide chlorine is attached to another carbon atom of the alkene. So ethylene chlorohydrin, and ethylene chlorohydrin reacting with alcoholic KOH, and then this HCl will be removed, and then we get ethylene oxide. Okay, and if you take another example, cyclohexene reacting with the hypochlorous acid, chlorine and water, then again we are getting 2-chlorocyclohexanol, 2-chlorocyclohexanol, which is on reacting with alcoholic potassium hydroxide, then we get the cyclohexene oxide and HCl. Now let's just discuss how the ethylene oxide is manufactured. Ethylene oxide is an important compound, particularly from the family of epoxides. Ethylene oxide is the important compound. It can be polymerized to polyethylene oxides also, and it is manufactured on a large scale by passing a mixture of ethylene gas and oxygen, high pressure and high temperature, in the presence of silver catalyst. Okay, passing a mixture of ethylene and oxygen or air under pressure over a silver catalyst at 537 Kelvin, very high temperature and high pressure, then we get ethylene oxide. So this is the method normally employed for the manufacturing of ethylene oxide industrially. Now let's discuss the chemical reactions of epoxides. acid catalyst ring opening reaction. The ring opening reaction is the major reactions of the ethylene oxides or the epoxides. So here acid catalyst reactions are shown. So ethylene oxide is reacting in acidic medium, then we get hydrolysis, we get OH, we get glycol, ethylene glycol. Okay, so both position we get OH group. So both carbon atoms of epoxides we get OH group, so we get glycol. Okay, and if we use ethanol in acidic medium, then one carbon atom it will be an OH group and other carbon atom will be an ethoxy group. Okay, so we get 2 ethoxy ethanol. Okay, CH2 OH is ethanolic group, so this is 2 ethoxy ethanol. Okay, and then we take epoxide reacting with HBr, hydroboric acid, and we get one carbon atom of the epoxide is OH, and then this Br will go to the other carbon atom, so we get ethylene bromohydrine. Okay, and then if we react epoxide with acetic acid, again the same way, one carbon atom of the epoxide contains OH group and the other carbon atom contains an acetate group, CH3C double bond O group, that is acetate group. So this is glycol acetate. And then ethylene oxide reacts with HCN, hydrogen cyanide, and then we get one carbon atom of the ethylene oxide goes or converted or attached with OH group and other one with cyanide group. So we get ethylene cyanohydrine. And now let us discuss the mechanism of the reaction. The mechanism of the reaction involves a protonation of the epoxide. So first stage, the protonation, because we are conducting the reaction, we are doing the reaction in acidic medium. So in the acidic medium, the protonation of the oxygen of epoxide is taking place as the first step, which subsequently undergo nucleophilic attack by SN1 mechanism. Okay, second stage is an SN1 mechanism, that means a formation of a carbocation, and then attack subsequently a nucleophile is attacking on the carbocation. Okay, so in the acidic medium, protonation is taking place. So the lone pair of electrons on the oxygen of the epoxide will take up the proton, and then this will become O plus H. Okay, and then carbon oxygen bond cleaves in order to neutralize the charge over here, and this is the slow step, and then we get OH on this carbon atom and a carbocation is formed here. Okay, subsequently the nucleophile come and attack the carbocation, then we get the nucleophile attached to this carbon atom. So this is how the reaction shown here has taken place. Okay, next we have to discuss the orientation in the cleavage of unsymmetrical epoxide. Orientation in the sense the ring opening is possible in acidic medium and also in basic medium. So but the orientation is different. For example, when we take a compound like this, isobutylene oxide or isobutylene oxide or 2,2-dimethyl epoxide. Okay, 2,2-dimethyl epoxide. It is reacting with the methanol in the presence of acidic medium. Here we are getting 2-methoxy, 2-methoxy, 2-methyl, 2-methoxy, 2-methyl, propane, 1, 2, 3, parent is this one, 2-methyl propane, 1-ol. Okay, and then the same compound reacts under a basic atmosphere, basic condition. Then we are getting 3-methoxy, 2-methyl propane, 2-ol. So the substituents were interchanged. Okay, so the orientation is different when we take a basic medium and an acidic medium. Okay, so this is the major difference. Next we have to discuss the reactions of Grignard reagent with epoxides. So we will discuss it in the next class.